welcome to another exciting episode of Advanced Level Chemistry here at Spain Park. Today is Friday, November the 14th. Oh my word, time's flying. Okay? Hey, and if you're enjoying these videos, please hit that like button. Subscribe. What are we supposed to do? So,
notification smash that bell.
Smash that notification bell. Whatever. Subscribe to my channel. I'm going. Hey, we might hit 250 here pretty soon. Okay. Yeah. Big money. At the conference I was with, apparently one of the AP presenters that was doing our conference, apparently he's got a whole bunch of videos that kids watch and whatever, and apparently he's a big deal. I didn't know who he was, but maybe someday I'll be that big deal. Okay, so Jay.
That's Jay. Oh, Jay, walk in this time.
Yeah.
Jay, don't move your hand.
Oh, yeah, well,
Just hold on. So go all the way along, okay, and maybe grab the part that's not already stretched out, whatever. So somehow or other, see if you guys can video this. Okay, I don't know if you can or not.
Just tilt it down, yeah.
Okay. So again, on Friday we started talking about the electron being treated like a wave. And if I send a crest and back and forth, they interact with one another. But if I don't have the right wavelength, see how it's kind of chaos? Remember, we had two types of interference: constructive and destructive. Constructive, when the wave comes back and I send another wave, if crest meets crest, then it gets double high, because one crawls over the top of the other. If trough meets trough, they go double low. But then we can have destructive interference, and what happens there? Say what, Luke?
Trough meets crest.
Trough meets a crest, and what happens?
They
They cancel out, basically get no motion. Okay? So normally we just kind of send a wave and we go back and forth and we get the chaos, but if I get everything just right, now I've generated what we call a standing wave. In this standing wave, right where you see the crest and troughs where it's going up and down, that's constructive interference. Crest is meeting crest, trough is meeting trough, and they're double high and double low. And then right there in the middle is where we're getting destructive interference, is where a crest is meeting a trough, and we end up getting no motion, a nodal region. Okay? Now notice that there had to be two crests. You couldn't have 2.5 crests, you couldn't have a third. It had to be a whole number of crests. So if I change the energy and get it just right again, now I have these three envelopes, 3 crests and troughs, and 2 nodal regions. But again, it has to be a whole number. Okay? Glad you guys thinking this is so hilarious. Okay? If I change the energy again, okay, now I have, but again, notice every time I have to get the energy just right to get a whole number of crests. Okay, good job, Jay. Thank you.
Nice job, Jay.
So Erwin Schrödinger got the exact same equation.
I know, I'm watching the video.
Okay, all y'all's giggling, it's all going to be on the video. Okay? So when Schrödinger got this exact same equation, but treating the electron like a wave. But the key is that again, there's only certain distances from the nucleus that the electron can form that standing wave pattern. Now we were just doing an X and a Y, a very simple standing wave pattern. When you go three-dimensional, it gets much more complicated. The math that he used is way above my head, way above your head. I mean, it's like calculus 15. I mean, it's just heavy duty. I mean, it's not really quite that. I mean, if you really need at least 4 to 6 semesters of calculus in order to really begin to understand the math behind what's going on here. Okay? And so again, I didn't ever have that math. So I'm trusting a lot of this just to be true. So we're going to start off in this, and we're going to notice again, he kept the idea of energy levels, that there's only certain distances from the nucleus that that standing wave pattern can form. So in your notes now, let's just kind of look at, kind of go through this. So we want to look at the quantum mechanical model. And we're doing the quantum mechanical model of the atom. That's one of the most complicated terms and things. A lot of today, and unfortunately I'm probably not even going to get through enough to where I can relieve it, there's going to be a lot of confusion today. And we may end up over the weekend leaving confused. That's very normal, and it's just kind of something that's going to happen. Monday, when I finish, and then by Tuesday, the confusion's going to fade a whole bunch. We're going to start. We won't necessarily understand. We'll understand how to apply everything. We'll never understand how did they come up with this and how does this really work, because at least you guys might. I just don't. But we're going to understand how it applies and how we're going to use it, and some of that confusion is going to go away. So I say all that, just don't get too horribly stressed that you don't understand everything completely. Now that doesn't mean don't try and fight through and try to understand as best you can everything I'm about to share with you. Okay? How am I setting this up? I'm selling this well, aren't I? Okay, getting you fired up, ready to learn this. Okay? So we're talking 1926, okay? Again, remember Bohr and all those, we're doing everything 1910, 1915, all that. So there's been a while in between trying to figure out the nature of the electron since Bohr figured out all of this. But Schrodinger was able to then treat the electron like a wave, but instead of saying that it's in an orbit, okay, instead he says that it's in an orbital. And now it took his work, and then down here at the bottom of this page, you have the Heisenberg uncertainty principle. And it's hard to put all this because these guys all work together, but the Heisenberg uncertainty principle says that a particle in motion, it's impossible to know the exact position and energy of the particle at any time. However, we talked about, again, my 100-mile-an-hour serve down the T. In Heisenberg's equation, which he won a Nobel Prize for, so again, this isn't just simple equations. They win Nobel Prizes for all this stuff that they figured out. So, I mean, it's just complex. But if my 100-mile-an-hour serve down the T, the uncertainty is very minuscule, immeasurable. We can pretty much know exactly where the tennis ball is, how fast it's going at any given point. You know, they watch it on video, they show all that, and it's no big deal. But when you get to the electron, traveling at the speeds of an electron, the more you find of one, the more you know its position, the less you know of its speed. The more you know its speed, by finding one, you got to change the other one. The uncertainty gets to be much greater. So now, instead of saying that the electron's in a fixed orbit like you learned in middle school, now it's in this thing called an orbital. And that's what these shapes are up here, is that this is an orbital. Instead of saying that the electron's following a set path, it's in this complex three-dimensional wave pattern in here, a standing wave, but all we know is the most probable place on where the electron can be. We don't know how it's moving. The Heisenberg uncertainty principle says that we'll never know. It's impossible to know how the electron's exactly moving in here. It's in some kind of three-dimensional wave pattern, but all we get... Oh, did you close my phone? Okay? When we look at this, okay? Ooh, doesn't that look exciting? You know how when you do a math problem, you take the square root of 4? Square root of 4 has two answers, doesn't it? Plus 2 and minus 2. So sometimes when you have an equation, you can have multiple answers. Well, with Schrodinger's equation, it's got this thing called psi. It's called a wave function. It's an equation, And when you get the answer to that, it really doesn't mean a whole lot to us, but if somehow, and again, I'm just trusting, you square that wave function, it gives a probability of where the electron can be around the nucleus. Okay? Each dot right here on this particular thing is not a different electron, but it's a different place where the electron could possibly be given a certain amount of energy. When we put in these in values into Schrodinger's equations, and then you plot it, this is your probability of where you can find it. The electron probability distribution. Okay? So then they end up saying, okay, well, where's the electron going to be? Well, the shape, we're going to draw the shape of this thing. It's going to kind of look like this. The electron can be in an area kind of like this, and we're going to kind of describe how we come up with these areas. But it's all a probability. It's just this. So these are all, we're saying this is the most probable place, given the certain amount of energy an electron can have, this is the most probable place it's going to be. And then they draw the shape to where, okay, here's the nucleus. Where it's most dense is where you're going to have the greatest probability of finding the electron. So we're going to draw the shape to make it look like this, but the electron really could possibly be way out here somewhere. We just know it's a 90% probability or so it's going to be in this shape. Kind of like fourth period, you got lunch, 90% probability you're going to be in the cafeteria. Could be in the courtyard though. You could be out visiting, the teacher making up a test. Who knows what you're going to be doing, but most of the time you're going to be in the cafeteria. Okay? I'm saying all this because all we know is the most probable place. So everything we're going to talk about is where is the electron, where's the most probable place we're going to be able to find an electron around the nucleus if it's given a certain amount of energy. So in Schrodinger's equations, okay, we're going to hold that thought. In Schrodinger's equations, okay, the electron is in these orbitals. It's the most probable place. You look at a ceiling fan, it looks like it's everywhere at once, but really there's space. Technically, you could put your finger up through it, but I wouldn't recommend it, okay? So, it's not a barrier, okay? It just gives us a model, something to help us visualize where the electron is going to be, and then we already kind of talked about Heisenberg. So let's get to the nitty-gritty here. These quantum numbers. If you say something is the principal, why is Dr. Esslinger considered the principal? So what? Why is she called the principal? It's the main. That's why I thought I heard somebody say it. She's the main. It's the principal quantum number. It's the main quantum number. It's the primary. It's the most important one. Okay? So the principal quantum number states the energy the electron is on. That's my N. Is it on the first energy level? Is it on the second energy level? Third, fourth, fifth, sixth energy level? Okay? So it states the energy level. It's got to be a counting number. That's again, it can only go from one fixed energy level to another. One fixed energy level to another. Okay? Now, this is just a nice little thing on any given energy. This is what you kind of learned in 8th grade. On the first energy level, you can have 2 electrons. On the second energy level, 2 squared is 4 times 2 is you're going to have 8 electrons. On the third energy level, 3 squared is 9 times 2 is you're going to have 18 electrons. Okay? But we're going to learn a little bit more in depth on why all that works out and what's happening here. So our second quantum number, there are 4 variables in Schrodinger's equations, and all of them represent where the electron is going to be. Let me put it like this. You have been to a fancy hotel? Let's say it's a 30-story hotel. And you get a room and you're assigned room 2311. Okay? 2311. Where are you going to go? I know, but probably 23rd floor. When you get off on the 23rd floor, you're going to probably get off the elevator and there's going to be a little sign on the wall that says rooms 2301 to 2310 down this hallway, 2311 to 2320 maybe this way, 2321 to 2330 are going to be down this way. So you figure out, okay, I'm on which floor am I on? So which hallway do I need to go down? And then in that hallway, there's going to be a variety of rooms. You got to figure out which room you're going to be in. And most hotels, it's occupied. Our hotel is going to be a maximum of 2 people in any room. Okay? So our quantum numbers are going to be giving us our room numbers, so to speak, our quantum code. Where is the electron? What energy levels it's going to be on? And we're going to find it's going to be these sublevels. Well, the azimuthal or angular quantum number L gives me that sublevel. Now, I thought azimuthal was kind of a chemistry term for so long, but I moved from Baton Rouge, I moved to Chelsea. When I moved to Chelsea in 2001, Chelsea was still very much a little country town. Cable hadn't made it there yet. I had to get a satellite dish. Satellite went out one day, and I went and had to look up the settings. I thought, I could fix it. Yeah, like I could fix it. But when I was looking at that, it said the azimuthal coordinate system. I said, azimuthal? I thought that was a chemistry term. Didn't have internet back then. Well, we had dial-up, but it was super slow. Okay? So, I go to my 1963 World Book Encyclopedia set that I have at my house. And I look up, that's how we used to have to do research, by the way. We couldn't just say, hey, Google, hey, Siri. We actually had to look things up in an encyclopedia and do research, okay? But it said that the azimuthal coordinate system is a 3-dimensional coordinate system for satellites in space. So an X, Y, Z coordinate system around in space. So where is that satellite in reference to where I am right here? X, Y, Z. Where is that satellite going to be located so my satellite dish can point to it? Well, that's what this is. I have an electron going in a 3-dimensional space around the nucleus. Where is it going to be? Where is the most probable place it's going to be in my 3-dimensional XYZ coordinate system? So, but again, we can only have fixed energies. So L is dependent upon the value of N. These two are related to one another. You guys have maybe done math problems where X and Y are, Y is a function of X, to where Y is dependent upon the value of X or something like that. So L can only equal from 0 up to N minus 1. All right, it's going to get deep right here, so stay with me. Don't fade out. I need 100% attention. So if N equals 1, and I'm just going to I'm going to have to combine a lot of things all together here, and it's all written down, but I can't put it all together. If N equals 1, L can only equal from 0 up to 1 minus 1, or from 0 to 0, which means L can only equal 0. Okay. Schrodinger had to limit the amount of energy. The electron cannot gain or lose random amounts of energy, only fixed. So all of these are limiting the energy the electron can have. L can equal 0. When you plug in N equals 1 and L equals 0 into Schrodinger's equations, and you plot what that's going to look like, you get a plot that has a spherical shape. All those dots that we just looked at, when you plot the square of this wave function, it's a spherical shape. So this is the shape of an s orbital. Okay? So hydrogen only has 1 electron. So it's going to be, the nucleus is on the very center. It's a little dot in the center of this sphere. The electron's going to be buzzing around, and there's a 90% chance we can find hydrogen's electron buzzing around in a space that's going to look like this. Is it confined to this space? No. It's just the math says that most of the time it's going to be in a 3-dimensional spherical shape. Okay? Now, I'm going to jump to the third quantum number. Okay? Because the third quantum number is m sub L. And m sub L can equal from minus L to plus L. Again, they're all related to one another. I'm probably on the next page if you look for m sub L. Okay, you can put it all right there, but I mean I described the m on the next page. Okay, but m sub L is minus L to plus L. So if L is 0, what's minus 0 to plus 0 going to be? 0. M sub L can only equal 0. Now the fact that it equals 0, the is meaningless. The fact that it only has one answer is what's important. Because look, it's telling me the orientation in space. A sphere. No matter how I change this in space, no matter how I turn it, it's always going to be the same. There's only one possible orientation of a sphere. Only one way you can put it. Okay? So M sub L tells me how many different orientations in space are there for that particular shape. For an S, there's only one. But if I go to N equals 2, if I go to the second energy level, now I'm coming up to here. Well, L can equal from 0 up to N minus 1. So it can always equal 0, which means again I can have another spherical S sublevel. Oh, and it's called S. I didn't tell you that. It's called S. And it's in the notes. It says that it's an S in the notes, but okay. And again, M sub L can only equal 0. And the S doesn't stand for spherical, and I'll tell you that in a second. So here's a 1S. I know. Here's a 1S. Here's a 2S. What's the only difference?
It's bigger.
It's bigger. Because I'm on the second energy level now. Now, you guys know what those Russian dolls look like, where you have one and then you open it up, there's a smaller one on the inside, you open up the smaller one on the inside. Okay? You have to imagine this to be that. This needs to go on the inside of this. Okay, so I wish that this was cut in half, I could pop it open and put this in. The nucleus is a dot in the center of this one. So I have some electrons buzzing around here, and then I have an empty space, a nodal region, and then I have more electrons buzzing around here in a bigger sphere. Okay? So on the second energy level, so here's my nucleus. On my first energy level, my 1s, but now I go to my second energy level, I have a 2s, a bigger sphere. Okay? Now there's this region in between is where I have that destructive interference, where there's nodal region, there's no electrons. So the electrons are going to be this distance from the nucleus, and the electrons are going to be this distance from the nucleus. Nothing, well, very low probability in between. Okay? But when n equals 2, L can also equal 1. And that corresponds to a p sublevel, p orbitals. Now that's one I showed you the dots on. Some reason, some way, if I plug in n equals 2, L equals 1 into Schrodinger's equations, plot where the electron is going to be, it comes out into a shape that looks like this. However, this is very directional. It's very axial. So the reality is it could be on the x-axis, it could be on the y-axis, and it can be on the z-axis. 3 different orientations that this could be. This shows up in my M sub L. Okay? Well, if M sub L, it's on the next page, M sub L equals minus L to plus L. Well, if L is equal to 1, what can M sub L equal? From minus L to plus L. What's minus, if L equals 1, what's minus L going to be? Negative 1, 1, 0, and 1. 3 answers. Again, the fact that it's negative 1, 0, and 1 is meaningless to us. The fact that there's 3 answers. That tells me that there are 3 orientations in space, X, Y, and Z. All 3 are equivalent. They're all the same shape, just different orientations in space. So when you look at them, they're here, here, and here. X, Y, and Z axis. So these would all be superimposed on one another. So on the second energy level, not only do we have an S, so electrons there, they can be in the P, that's your PY, they can be on the px, and they can be on the pz. So just looking at this, it's going to look like the electrons are all just in this sphere. But the reality, they're very subdivided on where they can be based upon their energy. The electrons aren't just going anywhere in the cloud. They're very much confined. But they're not in an orbit like the Earth around the sun, like you learned in middle school. They're in some kind of three-dimensional. These are just the probabilities of where we're going to find the electron given a certain amount of energy. The energy is dependent upon the values of these quantum numbers. So, if I go to the third energy level, N equals 3. Now what can L equal? L can always equal. L can equal from 0 up to N minus 1. So what can L equal? 0, 1, and 2, right? So L equals 0 still corresponds to an S orbitals. And there's just going to be one of them. L equals 1 still corresponds to my p orbitals, or sublevel. And now L equals 2 is going to correspond to d orbitals. Now, what can m sub L equal here? If L equals 2, what can m sub L equal? Always from minus L to plus L. If L equals 2, negative 2, negative 1, 0, 1, 2. Now, again, what those numbers mean is irrelevant. But the fact that there's 5 answers, the fact that there are 5 answers tells me that there are 5 different possible sublevels, okay, on the D, 5 different orbitals on the D sublevel. They all have these different arrangements, okay? They're much more complex. Let me realign that. They're much more complex. If you want to look at the shapes in a book, they're going to look like that, okay? Each one of these is one orbital. We call them rose petal shape, okay? Okay? They're going to look like this, but there's just 5 different ways that these can orient themselves. They're all what we call degenerate orbitals. Degenerate simply means equal energy. Now, I don't know how one word can have completely different meanings, because most of the time a degenerate is socially, worthless person. He's a total degenerate, not worth anything. But in this case, degenerate means equal energy. Okay? So there's 5 of them. This one would be like this one maybe. They're all on the different axes. Notice, see how this is on the X and the Y, the X and Z. It could be like this, like that. There are just 5 different possible orientations in space. Okay? It's very complex. These are what the dots look like. So this is the probability. This is when you square the wave function. You put in n equals 3, L equals 2, m sub L equals, let's just say m sub L equals minus 2, and you're going to plot where the electron's going to be, and it's going to show up like this. M sub L equals minus 1, it's going to show up like this. These are just the different orientations in space, where the electron's most probably going to be. Again, high-level math. All of this is pretty complicated. So if I'm going to go and try to go here, n equals 3, well, I'm going to go to a bigger sphere. Okay? This is 3s. Bigger sphere. Now it's supposed to be round. It's not supposed to be flattened like that on this side, but I'm not a very good artist. Okay? And I'm going to have 3p. It's just going to be a bigger orbital. Bigger orbital. And then, if I tried to put my D's in there, I'm not a good enough artist to be able to draw the 5 D's, but they would all just kind of superimpose. And so again, it's going to look like just one big sphere of electrons, but the reality is they're all going to be very subdivided within the electron cloud, where they can be based upon their energy. Now, this model gets very complex, so we need to simplify it, okay? And we can simplify it by just simply saying, okay, on the first energy level, I can only have one, L can only equal 0, and when L equals 0, there's only one possible orientation, one orbital possible on the S sublevel. So I'm just going to draw one line, and I'm going to try to make it go horizontal, and I'm going to call that my 1s. And this is going to be increasing energy. And you guys are going to want to copy this down probably on the last page of your notes. Okay? So in my first energy level, I can only have one possible sublevel, the S, and on the S sublevel, there's only one orientation or one orbital, so I draw one line. But I go to the second energy level. Well, when n equals 2, L can equal 0 and 1, which means I can have an S and I can have a P sublevel, but I have 3 possible orientations, -1, 0, and 1. So I can put those over here as my 2P. Now I go to the third energy level. I can have an S. I can have my P, my 3P, but I can also have a D. How many orbitals are there on the possible different orientations? 5. Okay? 1, 2, 3, 4, 5. 3D. Okay? Now, we're going to use this model for all of our atoms. We have one more quantum number. And that's called our spin quantum number. And this is known as the Pauli exclusion principle. He won a Nobel Prize for this too. Okay? And he found out that electrons have a spin. And you can think of them like spinning on, like the Earth spinning on an axis. That one spinning clockwise and one spinning counterclockwise. Now, spinning charged particles generate a magnetic field. If they're spinning opposite, they generate oppositely charged magnetic fields, which allows electrons to occupy the same space. But he said only 2. You can only have a clockwise, counterclockwise. You can only have a positive and negative. The value is +1/2 and -1/2 in the equation, but the plus and the minus is what's important. And so we represent that with arrows. So hydrogen has 1 electron. I'm going to say it's an up arrow. That's spinning one particular direction. Okay, hang with me. So hydrogen is 1 electron. The nucleus is in the center of this. Hydrogen's got 1 electron. So we know it's in some kind of 3D pattern, 3D wave pattern, staining wave pattern. But it's going to be in the spherically shaped area close to the nucleus. Helium has 2 electrons. So the second electron is going to go in the same space, but it's going to have an opposite spin. So helium's got 2 electrons that are in this s orbital, float in a 3-dimensional staining wave pattern somewhere in here. How's it moving exactly? We don't know. Heisenberg says it's impossible to know. But we're going to have 2 electrons down close to the nucleus. But notice, helium's at the end of that first row, because my first energy level is filled. So if I go to lithium now, I come back over here right below hydrogen. Lithium's got 3 electrons. So the first 2 are going to be down here in this, down here. You got 2 electrons in here. You can just put it anywhere here. So now lithium's got 1 electron out here in this bigger sphere. So 2 in here, 1 here. Now beryllium's got 4. So the second one is going to go in here, but it's got to have an opposite spin. So beryllium's got 4 electrons. So 2 of them are going to be buzzing around down in here, and then the other 2 are going to be buzzing around in here in some kind of 3-dimensional wave, standing wave pattern, but they're going to have this opposite spin. Okay? But notice now that there's kind of a jump between beryllium and boron on the periodic table, because now boron's got 5. So the 5th electron, this one's filled, so the 5th electron has to go up in here into my P. So now it's going to have to go into a different energy. It's going to take a different shape completely, a different pattern completely. And so now we're going to pick one, anyone, all 3 of these. The X, the Y, and the Z, they're all equal. So I'm just going to put an electron here. And when we come in on Monday, we'll just finish this up and kind of talk about how do we go all the way out for every electron. And it's okay. It's okay if you don't get all this. We're going to keep working through it Monday and Tuesday. I promise you by the end of Tuesday, you're going to feel much, much, much better about this. But for right now, you guys have a wonderful weekend. Be careful if you're going down to Sierra Land, and go Jags.